For nearly a century, cosmology rested on one quiet assumption: that the universe, at its deepest level, had finished changing. Galaxies moved. Stars were born and died. Space expanded. But the background, the ancient structure behind everything, was fixed. That background has a name. It is called the cosmic microwave background, or CMB. And it was never supposed to change again. The CMB is not a theory. It is not a simulation. It is measured. First detected in 1965, it is the leftover radiation from a universe only 380,000 years old, long before stars, planets, or life existed. For decades, missions like NASA's COBE, WMAP, and later European Space Agency's Planck satellite mapped it with increasing precision. What they found was reassuring. The background was almost perfectly uniform. Tiny fluctuations existed, but they matched predictions. Random, statistical, frozen in time. Cosmologists referred to it as a fossil. Fossils do not react. When the Planck mission released its final high-resolution maps, something subtle but disturbing appeared. Not in one place, not as a single spike, but as large-scale alignments. Regions of the CMB showed directional patterns, correlations that stretched across enormous distances. These patterns had names scientists did not like saying out loud: the axis of evil, low multipole alignments, large-scale anomalies. They sounded informal because no one wanted to formalize them too quickly. The reason was simple. If the CMB showed direction, then the universe itself might have a preferred orientation, and that should not exist. At first, these anomalies were dismissed. Instrument noise, foreground contamination, processing artifacts. That explanation worked until it didn't, because the same features appeared in different frequency bands, with different data cleaning methods, across independent analyses, and they aligned not randomly, but coherently. When multiple teams reproduce an anomaly using different methods, the word fluke starts to lose meaning. Something else had to be considered. While cosmologists argued about the background, another group of researchers were mapping something else. Not light, but absence. Large-scale surveys revealed enormous regions of space called cosmic voids. These are not small gaps. Some span hundreds of millions of light-years. Originally, voids were treated as passive, empty, irrelevant, but new data suggested otherwise. Certain voids appeared to correlate with CMB temperature deviations through a phenomenon known as the integrated Sachs-Wolf effect. In simple terms, light passing through these voids was being altered, not blocked, not absorbed, modified. Empty space should do nothing, but voids were not doing nothing. They were interacting with the oldest light in existence. This raised an uncomfortable question. If voids can influence the CMB, then the background is not isolated. And if it is not isolated, then it is not finished. When researchers overlaid CMB anomaly maps with large-scale structure surveys, some alignments were too precise to ignore. Cold spots, void boundaries, directional correlations. Each alone could be dismissed. Together, they formed a pattern that suggested feedback, as if the large-scale structure of the universe was not just evolving within the background, but acting upon it. That reverses the hierarchy of cosmology. And once reversed, it does not easily flip back. Then came the James Webb Space Telescope. JWST was not built to study the CMB. It was built to look forward into galaxy formation. Instead, it complicated the past. Webb's deep field observations revealed galaxies that appeared too massive, too organized, and too early. Structures forming faster than models allowed. This alone was surprising, but when combined with CMB anomalies, it suggested something deeper. If structure formation is accelerated or uneven, then the background conditions that seeded that structure may also be uneven. Which brings us back to the same question. Is the background still changing? Physics depends on stable foundations, constants, backgrounds, symmetries. The CMB represents the deepest foundation we can observe. If it is being altered, even subtly, then every derived model inherits that instability. This is not an extinction scenario. It is worse. It is epistemic erosion. Knowledge built on shifting ground does not collapse loudly. It becomes unreliable quietly. Other observations deepen the discomfort. Radio astronomers working with projects like CHIME and LOFER have documented unexplained background fluctuations at low frequencies. Not signals, not bursts, persistent noise structures, backgrounds within backgrounds. Each layer assumed stable, now showing texture. That is what makes this horrifying. Nothing dramatic is happening. No spikes, no explosions, no warnings. Just subtle, cumulative deviation. The universe is not announcing change. It is allowing it. If the CMB is being influenced by large-scale structure, then causality is no longer one-directional. The past is no longer sealed. And if the past can be altered, even statistically, then prediction becomes less reliable. Technology depends on predictability, navigation, timing, communication. So does civilization. There is a thought rarely stated explicitly in papers, but it exists. If the universe can modify its own background conditions, then it behaves less like a static stage, and more like a responsive system. Responsive systems do not require intent to be dangerous. They only require scale. The horror is not aliens, not entities, not intelligence. The horror is this: the universe may not be finished settling. And we built our understanding assuming it was. Everything discussed so far exists in peer-reviewed literature. Nothing here is fictional. But these are only surface anomalies. Deeper measurements, involving entropy, information preservation, and time asymmetry, suggest something even more disturbing that comes next. Because if the background is changing, then information itself may not be safe. And that leads us somewhere much darker. For most of modern physics, one principle stood above almost everything else. That information cannot be destroyed. Energy can change form. Matter can disperse. Structures can collapse. But information, the description of a system, was believed to survive. This assumption is so foundational that nearly all physical law depends on it. And now, quietly, it is under threat. In quantum mechanics, the idea that information is preserved is called unitarity. It is not optional. If unitarity fails, then prediction fails. If prediction fails, then physics stops being reliable. For decades, this principle survived every challenge, until black holes forced the question into the open. When Stephen Hawking showed that black holes evaporate, a paradox appeared. If a black hole consumes information and then evaporates into random radiation, where does the information go? This became known as the black hole information paradox. For years, physicists argued. Eventually, most agreed on a compromise. Information is not destroyed. It is scrambled beyond recovery. That answer was uncomfortable but survivable. The rule remained intact. What is rarely discussed outside research circles is this: signs of information degradation are now appearing where black holes are not involved at all. In cosmology, in large-scale structure, in background radiation, and that is far more dangerous. Entropy is often described as disorder. That definition is incomplete. Entropy measures how much information is lost when a system evolves. In an expanding universe, entropy should increase, but predictably. Recent cosmological models suggest something else. Certain regions of space show entropy growth that outpaces expansion. Not violently, gradually, as if information is leaking away faster than models allow. This has been discussed in relation to dark energy behavior, horizon entropy, cosmological event boundaries. None of these explanations fully close the gap. Every observer in the universe has a cosmic horizon. Beyond a certain distance, space expands faster than light can travel back. Anything crossing that horizon is gone, not destroyed, but unreachable. Here is the problem. If information crosses a horizon and can never return, is it truly preserved? Mathematically, maybe. Physically, functionally, no. The universe may be bleeding information permanently, not into nothingness, but into causal inaccessibility, which is indistinguishable from loss. Physics depends on testability. If information exists but can never influence anything again, it may as well not exist. This reframes the conservation argument. Information may be preserved in principle, but lost in practice. And practice is where civilizations live. This brings us back to the CMB, because it is not just energy. It encodes information about density fluctuations, initial conditions, quantum seeds of structure. If that information is being altered, smeared, or overwritten by later structure, then the universe is not just evolving forward. It is editing its own memory. One region of the CMB, known as the cold spot, has resisted explanation for years. Initially thought to be a statistical anomaly, later linked to a massive supervoid. But even that explanation does not fully account for its depth and shape. What makes it terrifying is this. The cold spot represents a loss of information density, not just colder photons, less encoded structure, as if something erased detail rather than added noise. Noise randomizes information. Erasure removes it. These are not the same. Multiple analyses show that certain anomalies reduce complexity instead of scrambling it. That suggests directional degradation, not chaos. Physics is comfortable with chaos. It is not comfortable with selective simplification. JWST observations complicate this further. Early galaxies appear too mature, too ordered, too complete. That means either structure formed faster than allowed, or the background conditions were already biased. If early structure had more information than expected, then later loss becomes even more concerning. Where did that information go? Put the pieces together. Background irregularities. Entropy behaving strangely. Information crossing horizons. Regions of reduced complexity. Individually, these are puzzles. Together, they form a pattern of systematic information degradation. Not catastrophic. Incremental. Quite. Sudden failure draws attention. Slow failure escapes notice. If the universe is losing its ability to preserve complexity, then advanced systems fail first. Not stars, not atoms, but long-range coordination, high-fidelity communication, precise timing, deep memory. Civilizations depend on these. The absence of signals is usually framed as distance or rarity. But what if signals are not disappearing? What if they are decaying into irrelevance? Not destroyed, just simplified beyond recognition. A message degraded until it becomes indistinguishable from background. This is the most disturbing implication. The universe does not need to destroy civilizations. It only needs to make complex states unsustainable. Life can persist. Matter can persist. But meaning does not. Information loss does not begin with explosions. It begins with memory failure, then coordination failure, then identity failure. By the time collapse is visible, the cause is long gone. No paper states this conclusion directly, but the math allows it, and the observations do not forbid it, which is the most dangerous position science can be in. Because if information degradation scales with distance and time, then exploration itself accelerates the problem. Every signal sent, every measurement made, every interaction adds strain. The universe becomes harder to listen to the more we speak. At this point, papers become cautious. Language softens. Footnotes grow longer. Because what comes next cannot be tested easily. But it can be reasoned. And reasoning leads somewhere dark. Technology assumes stability. So does science. So does prediction. If information slowly erodes, then certainty becomes temporary. Truth becomes local. And the universe becomes hostile without ever becoming violent. So far, we have discussed observable anomalies, theoretical boundaries, logical consequences. What remains is the most unsettling question of all. Not whether civilizations disappear, but how quietly they do. Because the final implication does not involve death. It involves irreversible simplification. And that is where this story ends. For now. There is a mistake people make when they imagine the end of advanced civilizations. They picture explosions, impacts, wars, or cosmic disasters that wipe everything out at once. But nothing in physics suggests collapse needs to be dramatic. In fact, most physical systems do not fail suddenly. They fail quietly by losing the ability to maintain complexity. Complex systems are fragile in a very specific way. They require stable information flow. They require memory, coordination, and long-term predictability. When those conditions weaken, the system does not die. It simplifies. And simplification is harder to notice than destruction. This is where the silence of the universe becomes unsettling. If the universe slowly degrades the fidelity of information, then complexity becomes expensive. Advanced technology depends on extremely precise signals, timing, and feedback. Small errors accumulate. Corrections increase. Energy is spent maintaining clarity rather than progress. Eventually, the system reaches a point where sustaining complexity costs more than abandoning it. At that stage, collapse does not look like extinction. It looks like retreat. This aligns disturbingly well with what astronomers actually observe. The universe is not empty of life-supporting conditions. It is full of stars, planets, and chemistry. What it lacks is evidence of long-lived, large-scale coordination. No galactic engineering. No persistent beacons. No stable, high-information structures extending across time. What disappears first is not life. It is ambition. This reframes the Fermi paradox entirely. The question is no longer, where is everyone? But, what happens when complexity becomes unstable? A civilization does not need to be destroyed to vanish from detection. It only needs to lose the ability to project itself coherently across space and time. Signals degrade. Infrastructure fragments. Long-term planning collapses. What remains is local, quiet, and inward-facing. From the outside, it looks like silence. This is why the universe may appear calm rather than catastrophic. Collapse driven by information loss produces no ruins, no explosions, no warnings. Just an absence of coherence. The stars keep burning. Life may even persist. But nothing large enough, organized enough, or stable enough remains to be noticed. This is not speculative fantasy. It is the natural behavior of complex systems under stress. Biology shows it. Ecology shows it. Information theory predicts it. Physics allows it. And now, cosmology is beginning to hint at it. If information degrades across cosmic scales, then civilizations that attempt to expand, communicate, or coordinate widely accelerate their own instability. The more they rely on long-range precision, the more vulnerable they become. Expansion does not save them. It exposes them. In that light, silence is not evidence of absence. It is evidence of adaptation. The universe does not need to eliminate intelligence. It only needs to make intelligence expensive. This is the most disturbing implication of all. The universe does not behave like a hostile force. It behaves like an environment with constraints. And environments do not announce their limits. They enforce them quietly. If this is correct, then the future of exploration is not blocked by distance, energy, or technology. It is limited by how much complexity the universe can preserve before it begins to smooth it away. This also explains why we are observing tension in fundamental physics now. Why background radiation shows anomalies. Why entropy behaves strangely. Why early structure appears unexpectedly mature. Why clarity does not scale with sensitivity. These are not separate problems. They are symptoms of the same boundary. The boundary where information stops being reliably preserved. And here is the final, uncomfortable thought. If this process is real, then it does not begin with advanced civilizations. It begins with the background itself, with subtle changes, with minor degradation, with effects small enough to dismiss. By the time collapse becomes visible, the cause is already ancient. We are not witnessing the end of something. We are witnessing the conditions that make endings inevitable. The universe does not erase history violently. It edits it until detail disappears. And the most terrifying part is this. Nothing in physics guarantees that we are exempt. If this explanation unsettles you, you're already asking the right questions.